Hey everyone, and welcome to The Explainer. I am super thrilled you're hanging out with us today. Look, we are tackling a fundamental concept in electrical engineering that, honestly, it feels a bit like a magic trick once it finally clicks for you. We're going to demystify the superposition theorem. If you've ever stared down a complex circuit diagram and felt just completely overwhelmed by all the moving parts, you are exactly in the right place. Okay, let's dive right in and learn how to literally divide and conquer.
Picture this. You're looking at a circuit, right? And instead of just one nice, simple battery pushing current through the wires, you've got two, or maybe even three. They're all pushing from completely different directions, creating these competing flows of energy. So pose this question to yourself right now. How on earth do you solve a circuit when power sources are actively competing? Do they just cancel each other out? Do they multiply? Figuring out what actually happens in the middle of that electrical tug of war is exactly what we're going to figure out today. So here's our game plan for today. We'll start by looking at the two-source circuit problem. Then we'll define the superposition theorem itself. After that, we'll analyze the 10-volt source, then the 5-volt source, and finally, we'll bring it all together by calculating the total final current. Pretty straightforward, right?
All right, part 1, the two-source circuit problem. Let's set the stage.
Take a look at the villain of today's story. We've got this rectangular circuit with a wire running straight down the middle. On the left-hand side, we have a 10-volt power source pushing current into the mix. Over on the right side, there's a 5-volt power source doing the exact same thing. And right in the middle of all this chaotic action is a shared pathway.
Let's break down the exact details of this setup so we know what we're up against. We've got those two voltage sources, the 10-volt and the 5-volt. Interspersed in the wires, resisting the flow of electricity, are three resistors. There's a 2-ohm resistor on the top left, a 4-ohm resistor on the top right, and a 6-ohm resistor sitting smack in the middle wire, which connects the top node, we'll call that node B, down to the bottom node, node D. Now, our ultimate goal today? We need to calculate the exact current, which we're labeling I, flowing downward through that center 6-ohm resistor.
Moving right along to section 2, defining the superposition theorem. Enter our hero.
Okay, so the absolutely crucial point is this. The superposition theorem tells us that in a linear circuit with multiple independent sources, the total response, meaning the total current running through that middle resistor, is exactly equal to the sum of the responses caused by each individual source acting totally on its own. Mathematically speaking, our total current I simply equals I1 plus I2. Basically, instead of trying to do one massive headache-inducing calculation where both batteries are fighting each other, we just solve two incredibly simple problems and literally just add the results together. It's brilliant.
So here is our highly strategic divide-and-conquer game plan based on that theorem. Step 1, we're going to analyze only the 10-volt source. And to pull that off, we literally just turn off the 5-volt source. Now, in circuit analysis, turning off a voltage source means replacing it with a short circuit. It basically just becomes a plain old wire with 0 volts. Then, step 2, we do the exact reverse. We analyze only the 5-volt source by shorting out the 10-volt source. Let's put this into practice. Section 3, analyzing the 10-volt source.
Notice how simple this circuit has suddenly become. Over on the right side, that 5-volt battery is just completely gone, replaced entirely by a short circuit, just a straight, flat line. By zeroing out that 5-volt source, we've successfully isolated the 10-volt source. So the current that flows down through that 6-ohm resistor in this specific isolated scenario is what we're going to call I1.
Now, to find that current, we apply KCL, Kirchhoff's currents law, right at that top intersection, node B. KCL simply states that all the currents leaving a node have to add up to 0. Let's look at the three paths leaving node B, okay? To the left, the current is the voltage at B minus the 10-volt source, all divided by the 2-ohm resistor. To the right, it's the voltage at B minus 0, because remember we shorted that battery out, divided by the 4-ohm resistor. And heading straight down, it's just the voltage at B divided by the 6-ohm resistor. We set all that equal to 0. See? I know it initially looks like intense engineering, but it's really just basic algebra.
Now we just simplify that algebra to find VB, which is our temporary voltage at node B. If we find a common denominator, we get 6 times the quantity VB minus 10 plus 3VB plus 2VB, and all of that equals 0. Combine your terms and you get 11VB minus 60 equals 0. Move that 60 over, divide by 11, and boom! We reveal a voltage of 60 divided by 11, which is 5.455 volts at node B.
Guys, we are incredibly close to finishing our first mission. We know the voltage at the top of the middle wire is 5.455 volts. And the resistance there is 6 ohms. Dividing those gives us our first current, I1, which comes out to 0.909 amps.
And because the voltage at the top is positive compared to the bottom, we know for sure that current is flowing downward. Half the problem is already solved.
Let's just take a quick breather and see how this builds toward our final answer. We've totally conquered the left side. With the 10-volt source active and the 5-volt shorted, we get a downward pull of 0.909 amps. Next up, we have to pit that against our second scenario, the 5-volt source being active while the 10 volts is shorted, all so we can solve for I2.
All right, time for the flip side. Section 4, analyzing the 5-volt source.
Once again, we're applying Kirchhoff's current law at node B, making the assumption that all currents are flowing away from the node to sum to zero. But notice how our inputs have totally swapped places here. The left path is now VB minus 0 over 2, because this time the 10-volt source is the flat wire. The right path is VB minus the active 5-volt source over the 4-ohm resistor. And that downward path? It remains VB over 6. The actual structure of the math is perfectly identical. We've just swapped the variables to reflect our new reality.
Let's quickly walk through simplifying this second equation. By finding our common multiples again, we distribute and combine to get 6VB plus 3 times the quantity V minus B minus 5 plus 2VB equals 0. This beautifully collapses down to just 11VB minus 15 equals 0. Move your 15 to the right side, divide by 11, and we find our brand new temporary voltage at node B. 15 divided by 11 gives us 1.364 volts.
Time to wrap up mission 2. We take that new node B voltage of 1.364 volts and divide it by our ever-present 6-ohm resistor. So 1.364 volts divided by 6 equals 0.227 amps. And hey, just like before, this current is positive, which means it is also flowing downward through the resistor. Pretty cool, right? Both power sources, despite being on complete opposite sides of the circuit, are actually pushing current down through that center wire.
And now, the grand finale. Section 5. Calculating the total final current. I really want to remind you of our hero formula from the very beginning of this explainer. Total current equals I1 plus I2. We just proved that complex engineering analysis ultimately just boils down to really simple addition. We take the 0.909 amps generated by the isolated 10-volt source, and we simply add the 0.227 amps generated by the isolated 5-volt source.
And there you have it, 1.136 amps. Because both of our isolated currents were flowing in the exact same downward direction, they stack on top of each other perfectly. The total current flowing through that center 6-ohm resistor is exactly 1.136 amps, flowing downward. We successfully broke an incredibly intimidating problem into 2 super easy ones.
Before we wrap up and head out, I want to leave you with a bit of a provocative thought. We just used superposition to effortlessly unravel a circuit with 2 competing power sources. But the thing is, this theorem, it doesn't have a limit. If superposition works this flawlessly for 2 voltage sources, how easily could it unlock circuits with 3, 4, or literally 50 sources? You just isolate every single one, calculate them out, and add them all up. It's an incredibly scalable, foundational philosophy for understanding really complex systems. Keep that in mind the next time you face a problem that just seems way too big to solve. Just divide it, conquer the pieces, and add it all back together. Thanks so much for joining me on this explainer, and keep learning.